Hi there and welcome to this next video in our Integrated Math 2 video series. This is the beginning of Unit 3 in this series, and in this unit we're going to kind of transition from more of a graphical approach to quadratics to more of an algebraic approach to quadratics, and so we're going to get into that today. Before we do, to kind of get into that activity, we're going to do these warm-up problems here, these 5. So take a second and see if you can do that. Okay, so let's go ahead and look at these. Number 1, which function has the greatest y-intercept? So in all 3 forms, the y-intercept is always the y value when x is 0. So no matter what, you can always substitute 0 in for the x value and see what y value you get out. It just so happens in standard form, which is the first one here, in standard form, whenever you substitute 0 in for x, this whole term becomes 0, this whole term becomes 0, and you're always left with what we call the c value. And so the y-intercept for the first one is the point 0, -1. In the second one here, again, you could substitute 0 in for x. It's not as easy as the first one, but you can still do it. When x is 0, this whole term is 0. So really it's 0 minus 1 is just -1. When this x is 0, 3 times 0 is still 0. So you're going to get -9. Multiplying those together, you're going to get +9. So the point 0.09 is there. So right now that's greater than -1, and so that would be the answers. But let's see what happens over here. Let's see, we get, again, when x is 0, it's not 17. I'll go ahead and throw that out there. The y-intercept is not 17. That's actually the y value of the vertex, so don't get those confused. So it's the y value when x is 0. So if we substitute 0 in here, 0 minus 4 is still -4. So -4 squared. That'd be -4 times itself. So -4 times -4 is 16. So we're going to get 16 out of that. Then multiply by -1 out in front. So it's going to be -16 plus 17 is actually going to be 1. So 0, 1. So if we go from least to greatest, this will be the least, and then this one, and then this is the greatest. So this function here has the greatest y-intercept. All right, number 2, what is 17% of 30? As we've talked about before, just multiply the 2 numbers involved without any trailing zeros. So it'll be 17 times 3. 17 times 3, let's see, 10 times 3 is 30. 7 times 3 is 21. So it'll be 51. Okay? And then adjust your decimal. 51 is obviously not going to be 17% of 30. So let's move the decimal 1 place and see if that makes sense. Let's see, 5.1. Let's see, 20% of 30, 2 times 3 is 6, so that would be 20% of 30. So that means 17% would just be under 6, which makes sense there at 5.1. All right, number 3, these last 3 kind of lead us into our activity for today. And so in number 3, it says 3 apples plus 4 apples is going to equal, of course, 7 apples. All right, number 4. 3 40s plus 7 40s is how many 40s? Well, that would be 10 40s, which is going to be 400. I guess you could multiply the 3 times the 40 and the 7 times the 40 and add them together, but the whole point is, if we have a multiple of a quantity plus another multiple of that same quantity, then we can add those multiples together and get, in this case, 10. And so it's kind of the same thought process as we did up here with the apples, only with numerical values here. Again, 3 sets of 40. So, because you could write this out as 40 plus 40 plus 40 plus 7 additions of 40 equals 10 additions of 40. So you have 3 40s plus 7 40s equals 10 40s, or 400. All right, so let's bring that same idea of adding the same quantities up here to down here. We have 6x squared plus 3x squared equals how many x squareds? And you're probably thinking 9x squareds. Well, let's go back and make sure we understand why this is. X squared is always equivalent to x squared, right? These are the same quantities. Just as 40 and 40 are the same quantity up here, x squared and x squared is always the same quantity no matter what value x is. So that's really important to note there. No matter what x is, x squared and x squared are always equivalent. So we have 6 of that quantity plus 3 of that quantity equals 9 of that quantity. Again, you could write x squared plus x squared plus x squared six times. Or over here you could write x squared plus x squared plus x squared. So you have 9x squareds adding together, of course, is going to be 9x squared. Okay? And so that's going to lead into our activity for today, which gets at our goal for today, which is to be able to add and subtract polynomials, kind of as we've already alluded to. And we'll define a polynomial here in just a minute. We'll multiply polynomials, and then we'll talk about something called closure and how polynomials are closed under what we call addition, subtraction, and multiplication. And so we'll talk about that here in a little bit. So that's our goal for today. All right, so let's start with addition and subtraction. But before we do that, let's go back and think about our definition of a polynomial. There are certain aspects of an expression that define a polynomial. One of those is it's a set of terms. So each term is separated by addition or subtraction. So this is a term, this one's a term, term. So we have 6 terms there. Another characteristic of a polynomial is it has a variable, and so these variables, you see x in here. Another characteristic is it has coefficients. That's what we call those, our coefficients. Coefficients can be positive, negative, rational, irrational, all kinds of different things. And then lastly, the exponents involved, so the exponents of our variables have to be what we call integers. Okay? Positive integers. So 2, 1, 3, 4, 5, 6, 7, 8, 9. All of those are integers. So it kind of has to fit that characteristic. We cannot have negative exponents, and we can't have fractions that have a variable in it. So, for example, if we have 1 over x or something like that, we cannot have that and it be a polynomial. Which makes sense because if we have a negative exponent, those are the same thing, right? So we can't have either one of those involved with a polynomial. All right? So now that we have kind of a definition of a polynomial, let's talk about adding and subtracting them. So the first one we have up here, you can kind of think of this being one polynomial and this being another one. And sometimes you'll see them actually separated out with parentheses here. But when you're adding, parentheses aren't necessary because you're just adding them all up. And so that's why I didn't include parentheses there. But just know that if you do have parentheses, you can just go ahead and add them up as if there weren't any parentheses. So what we're going to do is we're going to think about how we can simplify this and like we did in the warm-up, are there any terms that we can actually add together? So we need to go through and think about, are there any terms here that describe the same quantity in terms of, or a multiple of the same quantity? So we said that x squared and x squared are the same value, right? So if we have 4x squareds plus 3x squareds, that should be 7x squareds, right? Because this is x squared plus x squared plus x squared plus x squared. This is x squared plus x squared plus x squared. We have 7x squareds adding together. And we won't have to say it like that every single time, but it just shows why we can add those together. All right. Could we add, I don't know, for example, a 10x and a 3x squared? Could we add these together? Are x squared and x always the same quantity, no matter what value x takes on? It's not, right? The x squared is equal to x when x is 0 or 1, but those are not the same quantity when x is 2 or 6 or -1. And so what we're saying here is this top statement is equivalent to this next one for any value x takes on. So we have to make sure that these are the same quantity when we add them together for every single value x could be. So since x squared is not always equal to x, we cannot add these together, okay? Because we're not adding the same quantity over and over again. And a lot of people refer to this as like terms. X squared and x are not like terms. So therefore 3x squared and 10x are not like terms. So we cannot add them together. All right, so let's go ahead and continue on. So let's find a like term with 10x. Are there any terms that have x to the first in them, because those are the same quantity? Let's see, over here, oh yes, -7x. So we have 10x's minus 7 of them is 3 of them, right? And I'll throw this out there too. We're not adding their exponents, okay? We're adding the quantities together, just like 3 apples plus 4 apples is 7 apples, or 6x squared plus 3x squared was 9x squared. Okay, so we have 7x, -7x and 10x makes 3x. And then lastly, any numbers involved, we can add those together just like normal. So 4 plus 5 is 9. So I want to point this out here. This was you can think of it as one polynomial plus another polynomial equaled, this is another polynomial. So that's going to come back up later today, is when we add two polynomials together, we get another polynomial. All right, let's go into subtraction, because that can be a little tricky. We cannot just, take away the parentheses like we did up there because of this negative right here. This negative or subtraction here is going to be subtracting this whole polynomial. So you can think of it as subtracting each one of these. So we're going to have this polynomial minus this polynomial. And so there's a couple ways you can do this. I'm going to go ahead and distribute, this is what we call the distributive property. We're going to distribute the negative into this set of parentheses here. So we're going to get 3x cubed minus 7x squared plus 5x minus 10 minus 15x cubed minus 7x minus 4. All right? So we've distributed the negative, which what that's going to do is it's going to change the sign of all three of these terms. One way to do this, I'm going to show you two ways to simplify this. And this works for any addition and subtraction problem. One way you can do this is kind of underline your first pair that are the same. Maybe square the next pair. Okay, that doesn't have one. And then maybe circle the next ones that are the same, like terms. And then you can maybe, triangle, the last one. So you can maybe circle them with different shapes just to identify which ones are like terms, which ones we can actually add together. Another way to do it is to do like you normally do with subtraction. If we're taking this polynomial here and we're subtracting this one, you can just write this one underneath. So minus 15x cubed.
Bonus and PE and science.
Minus
You may come
7x
as computer.
minus 4. So notice I put the term underneath the one that it's going to add with or subtract with. So I put the like terms underneath one another so you can kind of easily see what's going to go together. So now we can actually go through and subtract them. So 3x cubed minus 15x cubed is going to be negative 12x cubed. Negative 7x squared did not have anything to go with, so it's still going to be negative 7x squared. Negative 2x and negative 14. All right, so again, a couple of different ways to do it, but be very, very careful with subtraction. You've got to take your time and subtract each one. So you might go through and say, okay, 3x cubed minus 15x cubed. 5x minus a negative 7x is actually a plus 7x, and just kind of think through it that way. But either way, be very careful with your negatives. In fact, that's the number one mistake we see on ACT, is involving negatives and things like that. And so be very careful, take your time with each step, right? So let me give you a second to try this one. This is another subtraction problem. We've got different powers of x in there, different exponents. So see what you can do there and take a moment and do that. Okay, so again, we're subtracting here. So the first thing I'm going to do, this is just how I would do this, is to distribute the negative, just so I ensure that I do it to every term here. And just double check that the signs, each sign changed. Okay, all right. And then I can add them together. So 8x to the fourth, do I have another fourth over here somewhere? Yes, right here. Right here's x to the fourth. So 8x to the fourth minus 6x to the fourth. So 8 minus 6 is 2 of them. Cubes. I only have one cube. So it's going to be negative 7x cubed. It didn't have one over here to add or subtract with. And then, let's see, do I have any squares? Okay, I've got one squared term, so it's going to be minus 3x squared. Do I have any x to the first terms? Okay, 4x, so that's going to go next. And then, do I have any numbers, or what we call constants? So that'd be plus 1 and plus 9, that'd be plus 10 altogether. So notice, I wrote this starting with the highest power of x, and just going down one exponent each time. And so that's what we call standard form, is when it's written in this order. If it's written out of this order, then it's not standard form. Okay, so just know that that's what we mean by standard form. Okay? All right, so let's move on to multiplying. Okay, so when we did adding and subtracting, when we added two polynomials, we got a polynomial out. When we subtracted two polynomials, we got a polynomial out. Let's see what happens when we multiply. And if we get a polynomial out when we multiply two polynomials. So this is, it's only two terms, but it's still considered a polynomial. Poly meaning many terms. This is still a polynomial. So we're multiplying, this is called a binomial, because it's two terms, and it's a linear, because it's only the highest power of 1. And this is also a linear binomial. So we're multiplying two linear binomials together. So let's see how this works. Some of you may have heard of a term called FOIL before, but I'm going to introduce you just to something called the distributive property. And I'll show you when maybe FOIL won't work here in just a minute. So when we distribute, we're almost undoing what we've kind of been thinking about. All right. So I'm going to rewrite this in a different way here. 6x times 4x minus 3 plus 1 times 4x minus 3. So if we think about what we've been doing, if we were to go backwards here, and when we started with this, we would say, okay, we have 6x of these plus 1 of these equals how many? And we would add, and we'd say, oh, okay, we'd have 6x plus 1 of these. And so we go back and say, oh, we have 6x plus 1 of these. And so we're just kind of going in reverse from what we've been doing. All right, so when you multiply two parentheses here, you're going to distribute and say, okay, we have 6x of these plus 1 of these. So kind of undoing the addition there. All right, so what we have here is we have 6x of these plus 1 of these. So 6x, what we can do here is we're going to distribute the 6x into this parentheses and then 1 into this parentheses. So we're going to get, let's see, 6x times 4x. Let's see, 6 times 4 is 24. And then here comes your exponent rules. X times x is x squared. All right? because x times x, you have two x's there, right? That's the definition of x squared, okay? All right, we also have to multiply the 6x times the negative 3. All right, we're going to multiply 6x times both of these. So 6x times 4x is 24x squared. 6x times negative 3 is going to be negative 18x. All right, then we're going to go over here. 1 times anything is just itself, right? So when we multiply 1 times 4x and 1 times negative 3, we're just going to get 4x minus 3. And then from there, what we're going to do is combine like terms. So we're going to have 24x squared. And then here comes our addition that we've been talking about. We have 4x's minus 18 of them equals negative 14 of them. Okay, so we combine those like terms. And this is standard form of a quadratic. Okay, so is that a polynomial? It is, right? It is, indeed. So when we multiply a linear times a linear, we ended up with a quadratic. That's going to be really key. That's how we get a quadratic, is by multiplying two linear expressions. If you remember back from the graphical approach to quadratics, we multiplied two linear functions graphically, and we ended up with a quadratic, right? Well, the same thing happens here. We multiply algebraically, we still end up with a quadratic. So kind of connecting those two representations can be really important. All right, let's hop down to this one. We have a quadratic times a linear. Let's see what happens. Again, 5x squared is going to be multiplied times this whole parentheses and 1 times this whole parentheses. So we get, actually I want to change this to 2 just to kind of mix it up a little bit. All right, so we have 5x squared times x minus 5 plus 2 times x minus 5. All right, so 5x squared, we're going to multiply in here. 5x squared times x is 5x cubed. Let's revisit that. X squared times x. Well, x squared is x times x. So we have x times another x is going to be 3x's. So that's the repeated multiplication definition of an exponent, right? So x times x times x is x cubed. All right. 5x squared times negative 5. So 5 times negative 5 is negative 25x squared. All right. And then let's multiply the 2 inside. So 2 times x is 2x. And 2 times negative 5 is negative 10. And we don't have any like terms here. Right? We have a cube, a square, a linear term here, x to the first, and then a constant. So we don't have any like terms here to combine. So this is our final answer in standard form. So again, we multiplied a polynomial times a polynomial, and we were left with a polynomial. Notice we started with a quadratic times a linear, and we ended up with a cubic.
Social Studies Department and World Languages, come on up for coffee and donuts.
So
and anyone else that hasn't made it, you may come on up.
So what that means is a quadratic times a linear equals a cubic, and that will always be the case. In fact, anytime you multiply by a linear, it's going to increase the resulting exponent by 1. So this was a quadratic times a linear increases that exponent of 1, and we end up with a cubic. So that's kind of a general way of thinking about it. All right. So with that, let's go and move on to our last little exercise for today. So let me give you a few minutes. I know we haven't seen one like either one of these. I want to give you a chance to try these. Just given what we've talked about so far, I want you to try both of these and just see what you can do. All right, so in this first one, what's different about this one is it has, we have a binomial, 2 terms, times a trinomial, which is 3 terms. So here's where your method of FOIL might be messed up here, because if you try to FOIL this, and for those of you that know FOIL, that'd be first times first, outside times outside, inner, which would be these 2, and then last, which would be these 2. But what happens to the 3x? We didn't multiply anything by the 3x. So that's what I mean by FOIL does not work anymore. So if you've used FOIL in the past, let's reconsider that and just call it a distributive property. Let's just distribute each of these terms into the second parentheses. So that's going to be equal to, if we distribute x into this parentheses, we're going to have x times x squared plus 3x minus 2 plus 5 times x squared plus 3x minus 2. And some of you might be able to kind of skip that step and just kind of think through like what would happen if we multiply all that in. But I like writing this middle step so you can see how it works. And then also, when we get to factoring in our next video, this idea here is going to come back and really help us of this second step here. Okay, so let's distribute x. So we're going to have x times x squared is x cubed plus x times 3x is 3x squared minus 2x. Basically, when you multiply a polynomial by x, every term increases its exponent by 1. Okay? Plus, let's distribute 5. So we have 5x squared plus 15x minus 10. And then now we need to go back and combine like terms. So we can simplify. See, x cubed doesn't have anything to add with. 3x squared and 5x squared makes 8x squared. Negative 2x and 15x makes 13x. And negative 10. That's it. So this is equal to this, is equal to this, is equal to this. These are all equivalent forms. They're all equivalent. We just have rewritten them in different ways. Okay? All right, and then lastly, down here, we haven't multiplied 3 things before, have we? We've only multiplied 2 parentheses before. So let me show you how this would work. With multiplication, you can pick to choose any pair of parentheses. I'm going to choose to multiply the last 2 first. And it really doesn't matter, but I'm going to choose to multiply these 2 together. So I'm going to pull out this multiplication here over here. So x plus 2 times x minus 3. So I'm going to multiply x into this parentheses and 2 into this parentheses. So x into the parentheses plus 2 into the parentheses. That's going to be x squared minus 3x plus 2x minus 6. So it's going to be x squared minus x minus 6. So this is equal to that, is equal to that, is equal to that. So this times this gave us this quadratic, okay? So we're going to put that quadratic here. And now we can multiply like we've done before. Just these 2. So just do 2 at a time, and you can kind of work through it, all right? So let's go ahead and multiply the last step here. X plus 1 times this quadratic here. So it'll be x times the quadratic plus 1 times the quadratic. And by the way, if this were a minus here, it would just be minus 1 times that quadratic. And of course, you'd have to multiply a negative 1 throughout. Okay, so if we distribute here, x times x squared is x cubed minus x squared minus 6x. Again, every exponent of x just increased by 1 because we multiply by a value of x. All right, and then 1 times anything is just itself, right? So this is just going to be staying the same. Now we combine like terms. X cubed minus x squared and plus x squared, those are what we call additive inverses. So meaning they add to 0. So we don't even have to write the quadratic piece now because those were additive inverses. And then of course negative 7x when we add these two together, minus 6. So these 3 multiplied equals, these 2 multiplied equals this, and then equals that. So those are all equivalent forms, or all equivalent expressions, just written in a different form. So if we recap here, let's go back up here to the top. And this is something you'll look more at in integrated 3. But when we multiplied 2 linears together, we ended up with a quadratic, right? If you remember from a couple of these ago. When we multiplied 3 together, look what we ended up with. We ended up with a cubic, which makes sense because along the way you can see we had a linear times a quadratic. which also ended with a cubic earlier. And so you can see that as well. But all in all, when we multiply polynomials together, we get a polynomial out, right? So we're going to talk about that in our last piece here. So this idea of closure is what we call that. So let's start with integers and show that integers are closed. So when we add two integers, 2 plus 7 equals 9. So this is an integer plus an integer equals an integer. Remember, an integer is what some people call a whole number. But it actually includes positive and negative whole numbers and 0. So I guess 0 is a whole number, but so for example, 1, 2, 3, 4, 0, negative 1, 2, negative 1, 2, negative 3, negative 4, negative 5. Those are all integers. So integer plus an integer equals an integer. How about integer minus an integer equals another integer? All right, when we multiply, integer times integer equals integer. So integers are what we call closed under addition, subtraction, and multiplication. Meaning, when we add integers together, we get an integer. Subtract or multiply, we all get an integer out. So if we think back to polynomials, we've talked about this already. Let me give you a second to try these three, just kind of as a final practice, and see what you get out. Okay, so for each of these, we're going to get polynomials. So in this first one, we're going to get, I'll just put this in blue, we're going to get 5x squared plus 13x plus 3. When we subtract, we're going to get negative 2x squared minus 3x minus 2. And then lastly, when we multiply these together, we're going to get 21x squared minus 4x minus 1. Let me just double check that here. Let's see, 21x squared, then we're going to have plus 3x, and then minus 7x, and then minus 1. Yeah. So that's going to equal 2x squared minus 4x minus 1. So when we added two integers, or two polynomials together, we get a polynomial. When we subtract polynomials, we get a polynomial. When we multiply polynomials, we get a polynomial. So just like integers, polynomials are what we call closed under the operations of addition, subtraction, and multiplication. What's not on that list? Division. We'll get to that in integrated math 3. When we divide polynomials, we don't always get a polynomial. So that's an example of something that's not closed, or polynomials are not closed under division. All right, so with that, hopefully we gained our goal for today, which is to add and subtract polynomials and to multiply polynomials. And then we'll talk about this idea of closure and how polynomials are closed under addition, subtraction, and multiplication. All right, so in our next video, we'll talk more about this idea, but in reverse. So we're going to talk about how to factor quadratics, and we're going to use a lot of these same ideas. All right, we'll see you then.